All right. So apologies. I'm sorry I can't be there in person. I'm sorry we can't all be there in person, but especially thank you to Elena, Leonid, Alexei, and all the GovCon Russia team for pulling this together. I'm really proud that I still had the opportunity to present to you, and I hope you find this interesting. So today we're going to talk about Go's hidden configuration variables. I thought that maybe this would be interesting for the audience, and also perhaps something that you probably hadn't come across in part of in just your every day-to-day Go programming. So before we talk about Go, and before we talk about this idea of Pragmas, let's go back in history. Many languages have the notion of like an attribute or a special directive, or maybe like a flag that can change the way that source code is interpreted during compilation. For example, Perl, for the old school Perl programmers, has the use directive, which enables, it's used to enable features or to make the compiler interpret source slightly differently, or something like that. Maybe it makes the compiler more pedantic, or maybe it just enables new syntax. JavaScript has a similar construct. In ECMAScript 5, they extend the languages with so-called optional modes. And when you have different modes, you need to know which mode the source code should be interpreted in. And so in JavaScript, you use things like use strict, which enables strict mode. The Rust fans in the room, they have a similar idea. They call them attributes. These little hash bracket things let you turn off and on features of the compiler or the standard library. For example, I took this example from the internet somewhere, and it says that superfast function is always inlined, or this macOS only module is only if you're compiling on macOS. So that's an example. And we can go back even further into history to find out what the word pragma means. The name that we take, Pragma, comes from Algol 68, the first block-scope language, which C and Pascal and Go and many of the other languages that we use today we think of. And they were called pragmats, which was short for the word pragmatic, the English word pragmatic to mean, pragmatic means, to be very literal, do this. When they were adopted by C in the 1970s, the name was shortened again to what we know as hash pragma. If you're a C or C++ programmer, you know the hash directives, hash include, hash define, hash pragma. And because of the widespread use of C, that's how we know them today. We call them pragmas. In this example, this pragma changes the memory layout of the T structure from what would be its natural layout, which is word aligned, to something more compact, so pack on a 2-byte boundary. The Pragma directive spawned a host of compiler-specific extensions, like if you've ever used GCC with the double underscore namespace or special GCC names. These are all kind of different ways that you can say in the source code to the compiler, do something a little bit differently, or do explicitly this rather than what you would just normally do. So now we know a little bit about the history of pragmas. Maybe we can ask the question, does Go have pragmas? We saw earlier that pragmas are often interpreted as like macros, or in C, they're like pre-processing macros sometimes, like hash include is a preprocessor macro. But this is Go. We don't have a preprocessor, we don't have macros. So the question is, does Go have pragmas? And the answer is yes, of course they do. Otherwise, this talk would be very short. And even though Go doesn't have macros or preprocessor, Go does indeed have pragmas, and they're implemented by the compiler as comments. They're actually, to just drive home like the lineage of this word pragma, in the source code, the name of the function which parses them is called Pragma value. Now, we're not going to discuss all of the ones on this list. We don't really have time, and some of them don't make a lot of sense. It's also important to remember, and I'll touch on it at the end, that this list does change over time because these aren't part of the language, they're part of the implementation. So let's have a look at a few examples just to kind of set the scene. So these are all taken from source code in the standard library. In this example, we have the Noescape directive, which is applied to the get time of day function from syscall. In some internal test data inside the compiler, we have an example of no inline, which we'll talk about a little bit later. It's one of the examples. In something to do with the pointer, the atomic storing of pointers, which is part of the garbage collector, we have an example of no split. We'll talk about that later again. You can see that like these are in use. Like if you have the Go source code, you can go and look for them now, and you'll find them not all through the compiler, but you know there will be a healthy selection of them. Which brings me to a word of caution. I said earlier that Pragmas are not part of the language. Like you're not going to find anything that I'm going to talk about today on golang.org. It's not in the spec. Because while they might be in a particular implementation, which we all use, they're not part of the language itself. And just as an aside, when these things came into use around the time of Go 1.5, when the compiler was rewritten from C into Go, there was not an insignificant amount of debate, especially after the first few had been added, which created kind of a precedent for more being added. And at the time, Rob Pike had this to say, said that like useful is always true for any feature request. The question is, does this usefulness justify the costs? When we talk about the cost here is the continued proliferation of magic comments, which are becoming too numerous already. I'll leave you to decide at the end of the presentation if actually the design path that the Go team went down was a good idea. So as we know now, the Pragma declarations that Go uses are placed in comments, and they have a very precise syntax. The syntax is, as you see on the slide, / go : the directive. Now, part of the design of this was that the Go prefix could be replaced with another. Like say you wanted to use this facility, or you wanted to just use this kind of convention for your own kind of thing. If you work with Kubernetes, you would see their plus K8S annotation that they apply to things. So even though the Go team, this is not part of the language spec, it's not a user supportable feature. At least they're thinking somewhat about future growth. It's also important to notice that there is no space between the slashes, the two slashes which start a comment, and the actual Go keyword. This is partly an accident of history. The person that first implemented this was the first person to implement it. They just chose not to have a space there. There's also, it also makes it less likely to conflict with a regular comment, which does have a space in that position. So you could write a comment about this Go directive without it being interpreted as the directive itself. And the last thing is that because these are not syntax, they're just comments, you'll most likely not get a warning if you get them wrong. If you misspell them or you have a space where you shouldn't, not even vet is going to pick up on these things. Okay, enough with the kind of warnings and the safety briefing and the pre-flight takeoff. Let's go and talk about the Pragmas that we have in the language. The first one I want to talk about is this one called Noescape. Early in Go's life, the parts that went into a complete Go program would include some Go code, obviously, some C code from the runtime back in the early days of Go, and quite frequently some assembly code, especially in the runtime and syscall packages. So the thing to take away from this is, while it was not common, it was understood that a single Go package, you'd occasionally find functions which weren't actually implemented in Go. And if you want to open up GitHub and go back to Go 1.2 and 1.3, you'll find plenty of examples of this in most of the common packages. There'll be a little bit, just a little bit of glue code or something implemented in assembly. Now, normally the mixing of languages wouldn't be a problem. I mean, this worked well for years, except when it interacts with escape analysis. So when I talk about escape analysis, let's have an example. We have a function called new book. It makes a book value and returns the address of that book, the address of B, to the caller. Now, we do this in Go so often that you're probably thinking at this point, fantastic, why do we have this guy keynote? Like, this is the simplest thing ever. But it's important to know that even though we do this as a matter of course, if you did this inside C, if you wrote this function in C, all you would get from this is massive memory corruption, because the address of B that you'd returned would be the address on the stack, which has now been overwritten by something else. And congratulations, your program is now in undefined behavior. So obviously in Go, this is safe, and this is safe because there is a process called escape analysis. The address, the value of B, because it lives longer than new book, it will be allocated on the heap, because that's the way to make this function safe. And this is a process called escape analysis. The compiler can see that the lifetime of B exists beyond new book, and so therefore the allocation for B escapes the lifetime of that function. This is why we call this escape analysis. So let's consider a slightly different version of this. We have this thing called build library, makes a book, as it said, and we pass the address of the book into this function called add to collection. So previously we were returning the address of B. Now we're taking the address of B and giving that to another function. So the question is, does B escape to the heap? And the answer is, it depends. It depends on what add to collection does with that pointer to a book. For example, if it did something like this, if it just changed the property of B, we said the classification of this is fiction, that's fine. B doesn't, if we go back to the function, even though we've passed the address of B into add to collection, it hasn't left the body of build to library. So in this case, it generally doesn't escape. And this is a key performance optimization. It keeps more things on the stack, less things in the heap, less things to garbage collect. But what if add to collection did something like this? The value of B is appended to this available for loan, like it's a library system or something like that. And so the value of B definitely is live longer than add to collection. And in this case, the compiler can't prove that this allocation lives beyond its local use, and so it must allocate it on the heap. And so now you can see the answer to the question of does B escape or not depends on how it's used, and it depends on what the body of the function that it's passed to does. So let's look at, with that setup, let's look at how Noescape works. We know that the tree of functions below a single function affects whether the value escapes or not. So let's consider this really, really common scenario. We're opening a file, we want to read it into a buffer that we've just allocated. So the question is this buffer going to be on the stack or on the heap? Now, if you were following along from earlier, the answer is, again, it depends. It depends on what read does. So if we look at there are no interfaces involved in here, so we know exactly what function f.read is. It's this bit of code from the standard library, which does some checks and then calls this lowercase read, which eventually falls down through a few more layers to the read syscall. And this is where things get difficult because syscall.syscall is not implemented in Go. It's implemented in assembly. And because it's implemented in assembly, the compiler, which only works on Go code, can't see what that function is doing. And so because it can't see what syscall does, it doesn't know whether values passed into it or not escape. And because the compiler can't know that the value might escape, it must assume, therefore, that it will escape. And so this was a problem that Go faced a long time ago. What we needed was a way of saying, for particular functions which aren't written in Go, for example, syscall, some assembly glue code, the bytes package like the equals and contains functions, MD5, time.now, all those little bits of glue which were written in assembly, we needed a way to tell the compiler, trust me, this doesn't escape. And so this was one of the first ways to, this was where Noescape came from. And this is precisely what it does. It says to the compiler, the next function that you see, it assumes that none of the arguments escape. There, of course, if the body of index byte actually does keep a reference to that value around you, you're going to have massive memory corruption. So it is a way. This does come with some risks associated with it, but the benefit is applied very strategically inside the standard library. Small buffers, which were previously forced to go on the heap because we didn't know where they were going, and now stay on the stack. Performance, big improvement. So the question you might be asking now is, can I use Noescape in your own code? And the answer is yes. Yes, you can, but only for 4 declarations. And let me just jump out of Keynote here and we'll have a look at an example here. Let me just make that slightly bigger. Okay, so when I say a forward function, this is what I mean by a forward function. It's a normal Go function that doesn't have a body. Like, there's no body. Where is the body? The body is implemented in assembly. And this is precisely the scenario that we were talking about before. Let me just actually remove or just comment that out for a moment. So in the length function, we take the second argument of the string, which is the length of the string. So the first argument of the string is the pointer to the actual data. The second one is the length, and we would just return that. That's effectively what the len function does. So if we run this, actually I need to run the whole package, we get 24 and 24, which is our length function and the built-in length function. But let's run this again and turn on inline printing. And we can see that on line 6, which let me just start. On line 6, which is this one, the parameter s is escaping to the stack. So even though, like, you saw the body of this, I don't keep it, but because the compiler cannot prove that because it can't see the source code, it has to assume that that string escaped. Let's add the Noescape directive, run this again. And you can see here that s no longer escapes the stack because we've said it doesn't. So there, just quickly, is an example of the Noescape directive. So you can use this in your own code. Let's talk about another one, no race. I'm just keeping an eye on the time. I'm doing good. Forking in multi-threaded programs is complicated. Because the child process gets a complete independent copy of the parent's memory, things like locks, which are values in memory, can suddenly, once that fork occurs, there can be two copies of the same program with locks in different states. Now, forking and execing in Go is handled with the, I'm just going to quietly mute you, Leonid. Nope, I can't. Someone else will have to mute you. Forking in Go is handled by the exec package, which eventually, calls down to the syscall package and calls the actual fork function. However, you're going to have to mute yourself. There we go. All right. However, when this happens, like this moment of forking execing is very, very has to be handled very, very carefully, because this is a multi-threaded program. And when the race runtime is in effect, this makes it even harder. To spot races, the race detector, when you compile in race mode, has rewritten it so that every read and write to memory goes through the race detector framework. And so that interacts with anything that reads and writes to memory, which is everything in the Go program. So what does no race do? Let's have a look at the commit. There is a special, this is inside the compiler, where we actually look as we're compiling and say, is this syscall dot function fork and exec in child? Inside the compiler, it knows specifically about this function and make sure that it's not annotated by the race detector because of precisely all of the problems that would cause. So prior to this annotation, the compiler knew had a specific check to look for exactly one function with this name. Afterwards, we added the no race detect annotation, which is only used in one place, and again has the same purpose. It says, this was in Go 1.6, it says, removes the special case from the compiler and replaces it with this no race directive. So should you use no race in your code? Maybe this should say, could you use no race in your own code? Let's have a look at an example. Okay. So we have a function here, main, which starts 5 Go routines and calls them all. We should really wait for it, but we don't need that for the example here. And each of the add functions is calling v++. Now, that's actually that, which is a read and a write. So this, given that this is running 5 Go routines concurrently, we expect this, when compiled in race mode, to generate a data race. And congratulations, there it does. So that's as we expected. Just as an example of, can you use the no race thing in your programs without it? Remember, all of this was what happened when the race time detected, the runtime detected a data race. Doing this again with the no race annotation. Congratulations, we've turned off the race detector function. It can no longer annotate it, so it can no longer see the data race. So to go back to the question, like, should you do this? No, you probably shouldn't use no race in your own code. It was added for a very specific function. It took out some complexity in the compiler and replaced it with a more general example. But the race detector has no known false positives. There are no cases where you need to fix the race detector by making it not worn on a particular thing that it finds. If you're in that situation, you shouldn't reach for no race. This was really only an example. You shouldn't reach for no race. You should actually fix what the race detector is telling you about. That's actually a bug in your program. Okay, moving on. We talked earlier. We talked earlier about Noescape. Part of Noescape is talking about the stack. Hopefully, if you've been around Go for a little bit, you know that part of the magic of Go is that Go's stacks are not a static allocation. Each Go routine starts with a few kilobytes and will grow and actually shrink over time if necessary. This is kind of the magic which lets us run hundreds of thousands, millions of Go routines, because they all, unless they need it, consume a very small amount of resources. The technique the runtime uses to manage the Go routine stack relies on each Go routine keeping track of its current usage. During the function preamble, this is just an example function. Every function in Go that is compiled with this has this little check, which you can see that the function has a size, which is the number of instructions in it. It has a list of the arguments that are passed into it, and this thing called locals, which is effectively, I need OX80 bytes of space to run this function. And so on entry to each function, the value is moved. This second line, move Q TLS to CX, is basically getting the Go routine ID out of TLS. And it's comparing the current stack pointer to the stack pointer that it expects, to the amount of stack it expects. If that fails, we JLS, which jumps down to the bottom of the function, which is basically a trap, to the runtime. We grow the stack, we restart the function, it does its check again, it finds it has enough stack space, it keeps running. So these are three instructions. They take, 13 bytes to encode. Generally, once the Go routine has warmed up, like it has grown its stack enough, this check always passes. And so it's easily predictable by the CPU. It's fairly cheap. But when we say it's cheap, there's a difference between being cheap and being free. And even this small check comes at a size of the program and comes with some execution overhead. And so one of the classic implementations, I just have some examples there. One of the classic implementations to improve program speed is to bring the body of a function into its caller so that you can avoid the overhead of the function call check. Okay, so just a quick digression. We're going to see an annotation called nosplit, and this comes from Go's original segmented stacks implementation. A long time ago, around Go 1.1 and 1.2, stacks would grow not by copying their memory to a larger space and then in the way that we know about append, they would grow in pre-allocated units. And so you would say the stack is split across several allocation units, and when a function needed to grow and needed to get a kind of new stack unit, that would always be some boundary which would cross. And programs became very, very sensitive to optimizations that the JSON benchmarks would constantly wave around by 20 or 30%, depending on these minor kind of like butterfly wing changes that would cause the functions to be slightly different places in the stack, and therefore the stack split check to happen at different times. So around about the time of Go 1.3, this was just all ripped out and replaced with the growable stacks that we know about, which is basically when you need to grow the stack, the whole stack is copied to a new location, which is larger, and we've done away with the segmented stack approach, but the annotation no split remains. So back in the old days, before the compiler was written in C, we used to have a Pragma called nosplit, which said to the runtime, you please don't put in the check for the split. Sometimes it was for performance reasons, sometimes it was for correctness reasons. Like we wanted to write this function in in a very particular way, and the stack split check would kind of break it. It's very common inside the runtime because the runtime can't call itself to write functions which can't take advantage of any runtime facility. So we needed a way of saying, for a particular function, don't do this. Yes. In modern Go, the Pragma has been replaced with this annotation called Noesplit, which does the same thing. But this leads to a problem. If you can write a function that says, please don't check the stack, just assume there's enough, what happens when you run out? Like I said earlier, that in the runtime, we actually use this quite a lot. And running off the end of your stack because you've disabled the checks would cause terrible memory corruption, especially like in the runtime, which is supposed to be the thing checking this stuff. So there has to be a way to turn off this check, but to do it safely. And to do this, the way that the compiler works is that you saw earlier, each Go routine has a little check to make sure it has the right amount of stack. If that check is disabled, as the compiler is compiling, it maintains this buffer. It's around about 700 bytes at the moment. It does change from release to release, which when it comes across a no-stack, a no-split function, it makes a mental note that, let's say, 30 bytes will be accounted for against this thing called the red zone, which is a guaranteed amount of memory in every stack that is available, even if you don't check. This applies recursively. So if you have a bunch of no-split functions, each calling each other, the compiler during compilation will keep track of, is it possible that this path through that compilation will run out of space? So let's have a look at an example of that. Just quickly get out of here. Where is my example? Red zone. So starting from the bottom, we have func main. It allocates a variable of type t, which is just a 256 byte array. It's not a slice, it's an array. So this value takes 256 bytes in memory. We then pass this value by value, not appointed to it, to A. A takes the t, passes the t to B, B passes it to C passes it to D, and at the end of the day, D actually doesn't do anything to it. So the thing I want to illustrate here is that each of these function calls is going to consume at least 256 bytes of stack space. Like when A passes the value of T to B, it copies 256 bytes to B. So let's try and build this. We see that we have a stack overflow. So assuming on the entry to main.a, we had 760 bytes of the red zone available. After main.a, we've used 264, so we're down to just under 500. After B, we're down to 224. And after C, calling D, we're now negative. So this program cannot be compiled safely, even if the no-split declaration is used. If we took these off, then of course this compiles fine. But something which I'll talk about next is, why do I have to use this no inline declaration here? This would be the point where I ask the audience, what do you think will happen? But instead, I'll just show you. And it compiles. But this is the same program that previously ran out of red zone stack space. let's have a look at the debugging information, and maybe that will give you a clue as to why this function compiles without that extra annotation. And the clue is because the calls are being inlined. Because the call is being of D is being inlined into C, is being inlined into B, inlined into A, the compiler can actually see all the way through and see that D doesn't actually do anything with the value of T that we pass to it. And so that code is removed. And so the call from C to D is removed, and the call to B to C is removed, and the call to A, and the call from A is removed. So all that, because the compiler can now see through, because we didn't disable inlining, it can now detect that we're not actually using T, and so all that code is just optimized away. And so that's why without that annotation, this compiles. Keep time. Doing good on my time. All right. So can you use no split in your own code? Of course you can. I just showed you. But it probably isn't necessary. There is a, I was going to say minor, but there is probably a measurable performance impact if you think that this is a very hot piece of code, but that is called a lot and you don't want to pay that function call overhead. But inlining, and especially now that we have mid-stack inlining, which I can talk about in the questions if you like, is far more effective at not just eliminating overhead of function call. It actually removes them because inlining removes functions entirely. So can you use this? You can in your code, but it's probably not necessary. Of all the Pragmas that I've shown you up to this point, it's the safest, as it will get spotted at compile time. You saw an example where I used too much no split, and the compiler said, I can't compile this. If you use it just randomly or sporadically in your program, it's not going to affect the correctness of your program. It may just have a performance impact. And of course, now this brings us to inlining. I just talked a little bit about it, that inlining reduces the cost of that stack check preamble by reducing the function call itself. Inlining is the classical optimization. Inlining lets the compiler see further. We saw in the previous example, when A and B and C and D could be inlined, the compiler could see all the way through, like 5 layers of function calls deep, to see that the value of T wasn't used and it could be optimized away. So inlining is kind of the bedrock, the foundation of all the other optimizations that happen after it. But what if you didn't want a function inlined? We saw an example just before. But this actually, no inline wasn't invented just to, like, for me to do party tricks. It actually had a real use. And it turned out that when Keith and the Go team were developing the new SSA backend, they did want to turn off inlining, in this case for small test functions where they wanted to write a function that tested only one particular aspect of the compiler, because inlining would kind of change the results and most often create incorrect code or crash the compiler. So they needed a way to turn inlining off, not using -N, which is where you turn it off globally, but just say, don't inline this function. This was the justification. Yeah, the code contained in that function might switch from being SSA compiled to being old compiler compiled. At the time that the SSA compiler was being developed, it only handled particular expressions, and the ones that it couldn't, it handed back to the old compiler. So without a way of knowing that this particular function would be compiled by the new compiler, they weren't sure they were testing what they thought. So this is part of the justification. And the actual, the decision to control what can be inlined is made by a function inside the compiler called isHairy. Hairy as in big, hairy problem. And at the time, although this has probably changed yet, this was a set of things which the compiler couldn't inline. Closures, ranges, fors, selects, switches, defers. This has changed over time, but this was the problem at the moment. So prior to needing this change, if you wanted to make a function non-inlineable, you just put an empty switch statement in there. Now, this empty switch compiles to nothing because you're switching on no cases, but it was enough to scare the compiler off and say, I won't try and inline this. Now, this worked great until you notice that until switch was removed from the list of hairy functions because the compiler got better, and all of a sudden they lost their way to say, please don't inline this function. Hence, that's why they needed no inline. Can you use no inline in your own code? Yes, absolutely. I showed you an example before. It tends to be useful in writing benchmark examples and example code and code, but effectively as this function says, please do a worse job of compiling this than you normally would. I can't think of any real world examples where you would need, where you would actually have used to use this in your own code, apart from, of course, examples. The last directive I'm going to talk today is called Linkname, which is unique in that it actually takes parameters. All of the others are just words, go no inline, but Linkname takes parameters. And it's the only example that I know that does. Here's an example of Linkname in runtime time ASM. For the longest time in Go, we had two ways of asking what the time was. We had the one that the runtime used for runtime type things, like if it needs to ask the time as part of the scheduler. And we had time.now. And every time we added a new architecture, new had to be added in two places, even though fundamentally it's the same code. Go to the operating system, make a syscall, get the current time, as well as all the other optimizations that getting the time has. So what Linkname does here is that it says runtime time underscore now and the time package now are, from the linker's point of view, the same. There are aliases for one another. You're not saying use this in another package. They are literally the same. So a function which used to live in one package now has two names, potentially in different packages. And if we look on the other side in the time package, we see that the lowercase now function, it says provided by package runtime. So that's how Linkname works. On one of those declarations, there'll be a Linkname declaration that says one name and another name are the same. They produce one symbol, and when they're referred to by either name, the linker will do the right thing. So the question is, can you use Linkname in your own code? If you look in the standard library, there's quite a lot of this, especially as the runtime package has broken out into multiple packages. It's a way of separating packages for kind of design and stylistic reasons, but also bringing them back together as they were just one giant amorphous mass. So can you use Linkname in your own code? The answer is yes. Although for this to work, because this allows you to sidestep the permission models in Go and the module system in Go, you are required to, as you saw in this example, import the unsafe package otherwise the declaration doesn't work. So let me show you an example of how we can do this. Because I asked, can you do this in your own code? Everyone knows that the Go routine has an internal identifier. This identifier is not exposed to Go code for a reason. The Go authors don't want you writing your own version of thread local storage. But this is an experiment. This is just a talk. What if you wanted to find out the ID of a Go routine? Word of warning, this is a party trick. Please never, ever do this in production code. As I said, this is basically a party trick. So that's on the other slide. Let's have a look at this example. We first of all print out the Go routine ID of the current Go routine. We add, we just start up a wait group, we add 5 to it. We run a bunch of other Go routines and ask them to print out their own Go routine ID. Wait till they're done. This is just good hygiene. Don't run a bunch of Go routines and then let your main Go routine exit. And then once we've waited for all those, I'm going to panic. And the reason for panicking will become obvious in a second. I need to. There we go. Okay, so this was our first Go routine. Excuse me. Oops. This is our first Go routine, and you can see we have 5 other Go routine IDs printed here. Are they correct? Well, let's see. We're looking for 20, 18, 19, 22, and 21. 18, 19, 20, 21, and 22. Other people have written this functionality actually parsing the output of the full stack trace, because as you see, the Go routine IDs are there. So how does this horror show work? As you see, the Go routine ID function comes from this package called bad idea. Where am I? We're in the bad idea. As you see, importing this package is a bad idea. Don't do it. But the Go routine ID function calls this thing called runtime get m. We cast it to an m. We get the current G, and then we get the current Go ID. So an M is the thread running a Go routine. Current G is the current Go routine it's running, and G Go ID is. How does this work? Let's have a look at runtime get M. You can see I use the, let me just make that bigger. I use the Linkname facility to link runtime get M, my function in my package, in the bad idea package, with the actual runtimes function get M. Now there's no checking here. I just happen to know, because I looked up in the runtime package, this returns a uint pointer. If you get the function call signature wrong, you get to keep both pieces. And the other part of this magic is that I needed to have enough of the M structure to find the current offset. So this is the actual M structure from the runtime package. We only need enough of it to get the pointer to the current G. We need enough of the G structure. So annoyingly, the Go routine ID is not stored at the top. It's stored down here. But effectively, runtime get M is going to return a pointer to an M structure. We need to go to the correct offset in that to get the G, and go to the correct offset in G to get the Go routine ID. So that's how this works. Should you do this in production code? Should you import this package? No, that would be a bad idea. But as an example of how Linkname works, and kind of a party trick, use it. Now, before I close, I know I'm running pretty late on time. There are many other pragmas that actually we use in Go code all the time that aren't part of the set. I haven't talked about them. For example, plus build. We call these build tags, ways of associating arbitrary nouns with source files so that we can include them or exclude them from the set that are passed to the compiler. We have Go generate, which uses the same syntax, but is not recognized by the compiler at all. It's used by the generate tool. We have the, what's it called? The canonical import path or something like that, which is just a comment, but it's interpreted by the Go tool itself to say, did you import this package in the correct place? Have you accidentally copied it to a place it shouldn't be? And the oldest Pragma in Go which goes all the way back to C, is line, which lets you change the line number associated with a particular line in the file. This is used in, we inherited this from the C compiler that Go was originally written in, but it's used, for example, when, like for example, the cover tool rewrites your code and so moves all the lines around. It then fixes up the lines with this line directive to put them back how they are, so that if you see you know, a coverage warning on a particular line, it actually goes back to the unannotated source code. So there's actually a lot of kind of magic comments and pragmas which we use every day in Go, which again, perhaps people didn't really give a full appreciation to. So that's my story. Pragmas in Go, like, they have a long history. I love telling stories that have a history, and hopefully that's been interesting to you. The wider arc is that these pragmas are used relatively sparsely inside the standard library. They're used to gain a foothold. As much as we want to write as much of Go in Go as we can, occasionally you reach this deadlock where the expression you want to write cannot be done safely in Go itself. So these pragmas give a foothold to the compiler writers and the runtime authors to let them out of that. Yeah, you'll find the pragmas used sparingly inside the standard library, but you'll never find them inside Godoc. They're not part of the language itself. Should you use these pragmas in your own programs? Possibly. Noescape is useful when you're writing assembly glue. I think it's probably the most useful one. It's used quite a lot in the crypto package, which they generally have some kind of core written in Go, glued together with core written in assembly, glued together with Go. But for the other pragmas that I showed you, I think for the most part they are illustrative. They're historical. They're kind of historical oddities. There probably isn't much call for using them in your code. Like if you're constantly reaching for these examples that I showed, there's a suspicion that maybe you're trying to do something that doesn't fit well with the ideas behind Go. Maybe another language would be a better choice. Or perhaps you're kind of applying magic kind of performance sprinkles, like that perhaps someone told you, always put this on your function calls, it makes them faster. That is clearly not true. And I want to close and leave you with the words from Russ Cox, which is, as I said, these are magic comments. They're not part of the language spec. If you use Go for JS or LL Go or GCC Go or Tiny Go, that code will still compile because these are just comments at the end of the day, but it may operate differently. And you won't get any warning, you won't get any kind of suggestion that you were making a mistake, because at the end of the day, these are just comments. And so I'll leave you with the advice from Russ Cox, who said, sometimes it's going to work, sometimes it doesn't. And if it breaks, well, I'm going to let you keep both pieces. So thank you so much. Thank you for listening to my talk. I'm so sorry I can't be there this year, and hopefully be there next year. I'm going to hand back over to the organizers, and we can take some Q&A. Thank you.
Thank you, Dave. Yep.
I'm just struggling because I can't find my mouse pointer. There it is. All right.
Okay, well, yeah, I can read the question. Who decides when to escape variable to heap, runtime or maintainer or both, in context of Go Noescape directive?
Sorry, I didn't quite catch that. Could you? Who decides when to escape a variable to the heap? The ultimate decision is the compiler. The compiler wants to keep small variables on the stack. It wants to, and that is part of the normal behavior. You saw me using. Let me just go back to. You saw me using the GC flags -m, which is going to tell that prints out inlining and escape analysis decisions, which is basically, this is what the compiler feels safe to do. So the answer to the question, I think the easiest answer is this is the compiler's decision. The one case that I showed that brings some of that power back into the author is when we know that the compiler can't see into that function because it's written in assembly. It can't know, and so we needed a way to push it in one way or another. Yeah.
Okay, next question. What about visibility of Pragmas in Go? Is it file or block or package level for next extraction?
It is none of those. It is the Pragma applies to the next. I'm going to say to the next function. It's basically the next declaration. So. Nope. To give you an example.
You don't share screen right now.
Oh, I'm sorry. I'm sorry. There we go. Okay, so to give an example, commonly they are written as close to the function as possible, but that will work as well if they apply to the next declaration. There is a Pragma which applies to variables, to type declarations, but it is only useful inside the runtime because the runtime is compiled with this special flag. So this basically applies to the next declaration. So they're neither file or package scoped, they're lexically scoped.
Okay, why there is no special syntax line like in C for Pragmas?
I don't know the real answer to that. Obviously, you can't start a line and go with a hash. So that's how we say in English, the hash, the pound sign. And I know that was one of the very first things that people complained about because they wanted to write Go scripts, like they wanted to be able to say, but this is not valid syntax. You can't start a line with a hash. So that's probably the most obvious reason why you can't do, why you can't do that. But probably the more nuanced one is that like those hash includes those hash directives have a strong association with the preprocessor in C languages, and Go doesn't have a preprocessor, so they probably didn't want anything that gave them the suggestion that it did. So I think you probably should ask Keith or Russ or Rob. That's my answer. Where does Go use? So I'm just going to. I can read the question. Where does Go use no race? It is only used in one function. It's used somewhere in the it's hard to. It's used in syscall exec. You saw a few examples up here. These are probably tests for that actual function, but it's used in that place to say, do not annotate this function for race detection because that's going to mess up. That's going to mess up something very, very, very delicate in the fork exec mechanism. So the answer to your question is use PT. By the way, PT is the Platinum Surfer. It's similar to ACK or Silver Searcher if you use that, but it's written in Go. It's written by a Japanese fellow called Monochrome Migan. No, I don't even have the source. If you're interested, I'll put the link to PT later on. But so answered that one. We talked about that.
Okay, there's a question in chat. It will be delivered by voice. Daniel. Can we enable the microphone?
So there are no raised hands at the moment, but if anyone would like to ask the question, yep, there is one.
Okay. Okay, Dave, you actually need to select one best question. We have a special prize for that person. One best question.
All right, I'll do that.
Wait.
I'll do that.
They're not done. They're not done yet.
Okay. We'll do that. We'll do that at the end.
Yeah.
Hello, Dave. Thanks for your talks. My question is about Pragmas. Why it hasn't other special syntax? It confused about comments have some effect for program execution or program compilation. Thanks.
Okay. Let me answer the question that I heard. Why is it this? Not that one. So why is it this special syntax? I don't know the canonical history. I can point you to the issue where this was first described. It's in the slides. They didn't want a space between the two slashes and the go, so that it was less likely to be mistaken for a comment, and also it would be less likely to type it accidentally, because generally when you're writing comments, and in fact GoFunct I think will add a space there for you. So I believe the syntax was chosen to make it less likely to accidentally activate this feature. That is the best of my understanding. I think the easiest way for me to do is to include links to the issues which was first discussed. You can read it yourself.
Thanks, Dave. Timothy, do you have anything to add or to ask more?
So just quickly looking at the other questions, will we have feature to create our own Pragmas in the future? Can we do it now? The answer to both of those is no. No, for probably two reasons. One, this isn't part of the language. It's not part of the spec. The second one is their inclusion was always somewhat contentious within the compiler authors. You saw the comment earlier from Rob, who was saying, do we have to have more magic comment strings? You have to remember that this man came from decades of C experience, which had exactly that, magic comments and magic hash includes, which changed the source code. So there was someone said, yeah, you can create your own linter. Oh no, actually, sorry. So there is no facility to add them, and really the attitude of the Go team has been they should not be the thing to reach for. Like they're needed to create escape holes. If you look for some of the Go Pragmas in the runtime, you'll see they're used a lot inside the garbage collector to do things like turn on and off the write barrier in the code that controls the write barrier, because otherwise there would be this kind of circular logic. But really they're meant to be these little escape holes for things which you just can't write in Go, which you would need to if you're writing the language itself. So hopefully that's a good example. Go ahead.
Sorry, Dave. I think we're out of time a little bit, but I have important announcement. We have coffee point, so we're going for a short break, but you can ask more questions to Dave at the coffee point room.